In this question, we're going to be looking at the idea of a reaction mechanism. A mechanism is simply a theoretical roadmap to show the electron movement between a starting material or starting materials and the product that they form. One crucial thing in mechanisms is understanding how we represent electron movement, since that's the purpose of the reaction mechanism. Chemists use a curved arrow to represent electron movement. A curved arrow with two heads on the arrow, like the one I just drew, shows the electron movement for two electrons. You may also see a one-headed arrow that shows the electron movement for one electron. Most of the reactions that you'll use in organic chemistry will deal with a two-headed arrow. So that two-headed arrow can show electron movement from either a bond or a lone pair. So in this specific question, the molecule on the screen is reacted with boron trifluoride. Boron trifluoride is a boron atom covalently bound to 3 fluorine atoms. If you look at the periodic table, you'll notice that boron has 3 valence electrons. So those 3 valence electrons can share another valence electron from fluorine to create the covalent bonds that you see there. So in any reaction mechanism, we have to understand how the electrons are going to be flowing. We'll be looking for where electron density is high and where electron density is low, and that will predict the flow. One thing you may notice immediately is that boron only has 6 valence electrons in the BF3 compound. Boron would like to have its full octet, but boron is 2 electrons short. So because of boron's electron shortage, that would be the most electron poor place on either of the molecules shown on the screen. If you look at the nitrogen-containing compound, we know that nitrogens have lone pairs, like the 2 I just drew in. The lone pairs on nitrogen are some of the more basic lone pairs on a neutral atom in an organic molecule. Nitrogen is small, and it's not exceptionally electronegative, so it has a reasonable desire to donate those electrons to other more electron-poor areas. If you look at this reaction, you've got nitrogen, which is electron-rich, and boron, which is electron-poor. If you remember your definition of a Lewis acid and base, we're actually doing an acid-base reaction. So the Lewis acid, or the electron acceptor, is boron trifluoride. The Lewis base, or electron donator, is the nitrogen-containing compound. And often, later in the course, you may hear the Lewis base being called a nucleophile. The Lewis acid you'll hear called an electrophile. So what we know about a nucleophile and electrophile, just like a Lewis base and Lewis acid, is that the electrons flow from the nitrogen, the Lewis base, to the boron, the Lewis acid. So let's draw those curved arrows to explain electron movement. So notice we're starting the arrow at the lone pair of nitrogen. So you start the arrow at where the electrons would move, and then you end the arrow at their destination. So that lone pair from nitrogen is forming a covalent bond with boron. So if we show the product of this reaction, there should now be a new covalent bond formed. Now that we've added an extra bond to nitrogen, nitrogen has 4 bonds. In its neutral state, it likes to have 3 bonds in a lone pair. With 4 bonds, it's missing a valence electron in the formal charge calculation. So nitrogen would be positively charged. Boron, on the other hand, has now added electrons from its neutral state, which makes boron negative. And you can review those calculations in the formal charges article. So that nitrogen, the nucleophile, or the Lewis base, attacked the boron, the Lewis acid, or the electrophile. And that's our first mechanism. Also notice, though, this molecule has another nitrogen. So another mechanism, very similar to the one we just showed, could be possible with the lone pair on the nitrogen toward the bottom of that compound. So let's see what that mechanism would look like. So again, we're talking about the lone pair on the nitrogen at the bottom of the screen. So that lone pair also could act as the electron-rich Lewis base. Again, you show the arrow moving from the area where electrons are in high density to the area where electrons are needed, like the electron-poor boron. So the product of that reaction will now create a 4th bond to nitrogen and a 4th bond to boron. So that lone pair is creating a covalent bond between nitrogen and boron. When drawing the product, we'll eventually see the bond formed between nitrogen and boron. The nitrogen, now with 4 bonds, would have a positive charge, like we saw last time. The boron, with 4 bonds, unlike its neutral state with only 3 bonds, will be negative charged because of the added electrons. So these 2 reaction mechanisms that we just showed were a really simple example of a Lewis base and a Lewis acid reacting together. We used curved arrows to show electron movement. We saw how lone pairs could turn into covalent bonds, as we saw from nitrogen to boron. And ultimately, we got our first practice showing electron movement. Since valence electrons are the most important part of organic chemistry, showing their movement to make or break bonds is an important concept to learn. Just like it's important to understand how electrons flow from areas of high electron density to low electron density.